So, Mohammed. Okay, I have to. Okay, that's good. Okay, so Al-Azhar remark 3.2.2. Okay, let's just look for, to start with, at the first inequality. Okay, so the first inequality is f L2D divided by D minus 2
Less
okay,
than
of
or equal.
RD is more RD smaller or equal than a constant which depends on S F in HS of RD.
But
Okay,
in the book,
and he
they
does.
didn't add RD.
They don't write RD, but I'm just writing it so that we know exactly in which
Uh-huh.
dimension we are. And also in the book they don't write, but this happens for any F which is in HS or RD. Okay, so what does this tell us? It tells us that if we know that F is in HS, or in other words, we know that this HS norm is finite, right? So let me write it this way. This says that, or this implies, it's better to say, this implies that if the HS norm of F is finite, right, then if it's finite, this norm here is finite, then a constant times this norm will also be finite. But this means this L to D over D minus 2 norm is also finite. So then F in L to D divided by D minus 2 is finite. Okay, but what does it mean for this HS norm to be finite? This means the same thing as F belonging in HS. And this other one, the L to D over D minus 2 non-finite, this means F belongs to L to D divided by D minus 2. Right, so we got this implication, in fact, and this is really the core. It says for any, okay, I should say if. Okay, so whenever F is in HS, then it means F is also in this L to D divided by D minus 2. So we have the following type of picture. Okay, after I draw it like this. So here I have, I don't even know where to write it. Okay, let me try to draw it here, like this. So here I have HS, a smaller space, and whenever I have a function, say f in HS, then automatically this also has to be in this L to D divided by D minus 2, right? So this L to D divided by D minus 2 is a bigger space, right? And HS is a smaller space, subspace of it. Okay, but that's not exactly what the theorem says. So let's really kind of get to what the theorem says. So far we showed that HS is included in this L to D divided by D minus 2. Okay, but we also know that HS is a subset of L2 if, let's say, if S is bigger or equal than 0. Okay, so that's something, you know, kind of follows from our definition. Is there any place where I can see it? Okay, let's see why this second thing, HS in a subspace of L2, is true. Well, okay, if F is in HS, then we know that this means that integral of 1 plus psi squared to the power s f hat of psi squared d psi, okay, to the power 1/2 is finite, right? Because this is exactly the HS norm of F. Okay, so we know this. On the other hand, I can show, but let's say 1 plus xi squared is less than 1, okay? Which means 1 plus xi squared to the power s is less than 1 for s bigger or equal than 0. So now, oh, sorry, it's not less than 1. It's bigger than 1. That's the whole point. It's bigger than 1. Okay, so what does this mean? It means the following. The norm of 1 times f hat xi to the power 2 d xi, let's say power 1/2, is less than the integral of 1 plus xi squared to the power s f hat of xi squared d xi to the power 1/2, which was the HS norm of f, and which is finite. Okay, but what is this? This is integral of f hat squared. So we know that this is the L2 norm of f hat. And by Plancherel, so we go back to properties of the Fourier transform. So Plancherel, this is the same as f in L2. Right? So what did we show? We showed that the L2 norm of f is smaller or equal than the HS norm of f, which is finite. Right? So this means in particular, all right, so f in L2 is finite, so f belongs to L2, right? So we showed here that whenever we have f in HS, in fact, f is also in L2. So we showed exactly this inequality. HS is a subspace of L2. Okay, so now we can do what is called, let's say we have seen this. We have seen this. So now we do something that is called interpolation. Maybe I'm not going to give details here, but let me write it this way. So we showed HS is in L2D divided by D minus 2, but also in L2. And by something called interpolation, which is a little calculation, so it's something you can certainly do. You get that in fact HS is embedded in any LP. Again, maybe to be rigorous, we should write RD. So the key point is this happens for any P which is between 2 and this 2D divided by D minus 2. Okay, and now if you look carefully, this HS embedded in LP, a subset of LP for all this range of P's, this is exactly, if I look at theorem 3.2.1, is what the theorem says. Right? So this is, I should say here, right? This is in fact, this is the statement of theorem 3.2.1. Okay, so this was
you forget S, but you D minus 2S.
2S. Ah, sorry. Yeah, I did forget S everywhere.
Yeah.
S. Sorry, just a second.
No worry, take your time.